Hi dears, good morning. Welcome to today's talk about electric dipole. In the previous session, we discussed about what is electric field lines, electric flux, Coulomb law, and superposition principle. These all we discussed in the previous session. And today's session is about electric dipole, electric field due to electric dipole, and the characteristics of electric dipole. Let's see the definition of electric dipole. Electric dipole defined as a couple of opposite charges of positive charge and negative charge, which are at to a distance apart from each other. So it is defined as both the positive and negative charges both are separated by a particular distance. So if the charge of positive and negative are separated by a distance, then this phenomena is defined as electric dipole. When we connect these two charges of positive and negative by a line, the line represents the direction of electric dipole in a space. So while we are discussing, the positive and negative charges are separated by a particular distance. So this separation with 2a distance is defined as electric dipole. If the two charges are positive and negative are connected by a particular line, the line represents the direction of electric dipole in a space. So this is about the figure for the electric dipole where the negative and positive charges are separated by distance d. Electric dipole is denoted by symbol P and it equals to product of charge and distance between them. The distance is considered as 2a, so the dipole considered as P equal to QD, where D equal to 2A, hence P equal to 2AQ. P stands for electric dipole, A is constant, Q is charge. So here it is denoted by symbol P and it's equal to product of charge Q and distance between them, where distance between them is considered as D. D is considered as 2A, hence P equal to QD and Q is nothing but charge, D is nothing but 2A, hence P equal to 2AQ. Next, electric field due to electric dipole. We know that what is electric field? The field which is influenced by or experienced by the charges is nothing but electric field. Now we are going to evaluate electric field in electric dipole. The electric field due to a dipole is evaluated from Coulomb's law and superposition principle. So how you are going to evaluate electric field? The electric field evaluated by Coulomb's law and superposition principle. The field due to electric dipole is also called dipole field. The field due to electric dipole is also called as dipole field. The electric field due to a dipole at a point can be found in two ways. How to find electric field at a point by the dipole? Yes, the electric field due to dipole at a point can be found in two ways. So these are the horizontals as well as vertical lines of directions. Positive and negative charges are separated by a certain distance. So what are the two ways? The two ways, if the point is axis of the dipole if the point is axis of the dipole. The second case, if the point is in equatorial plane of the electric dipole. If the point is in the equatorial plane of the electric dipole. Let's see case 1. Let us consider a point P at a distance r. What we are going to consider? We are going to consider a point P at a distance r from the center of the dipole. From where? From the center of the dipole. Then, due to negative charge, what is that? Due to negative charge, the electric field is considered as E minus Q. It is considered as E minus Q with respect to negative charge. Therefore, the negative charge electric field is considered as EQ equal to minus KQ by R plus A whole square P caps. R plus A whole square P caps minus KQ by R plus A whole square P caps, where R plus is a distance from a point from negative direction. R plus is a distance for the point P from negative charge. For the point P from the negative charge. So this is about the charge directions and point position and their distance we consider from this particular figure. Let's see. The electric field due to positive charge. Here you consider, you evaluate the electric field due to negative charge. That's the reason we taken minus KQ by R plus A whole square into P capsule because of negative charge. Now here the electric field due to positive charge is what? The electric field due to positive charge is considered as KQ, not minus. It is KQ by R minus whole square. R minus A whole square. R minus A whole square. Where the point is a distance of Ra minus A distance of Ra minus A from charge positive. From charge positive. So that is due to negative, that is minus minus KQ by R plus A square minus KQ by R plus A whole square. But due to negative positive charge, it is considered as EQ equal to KQ by R minus A. KQ by R minus A whole square. That is the difference between the positive and negative. Therefore, from the superposition concept, the net electric field at a point P, the net electric field at a point P will be the vector sum of the both the electric fields. Will be the vector sum of the both the electric fields. So this is about the axial line characteristics where the point is P. So positive charge and negative charge. Why you consider 2a distance? Because of so negative charge to center point is, it is considered as A. From the center to positive charge, it is considered as A. That is the reason in place of P we consider 2A. Sorry, in the place of D we consider 2A. So from negative charge to center is A. From center to point charge positive is A. So A plus A 2A. It's nothing but D. So the net electric field from the superposition concept, it is EQ plus E minus Q. So we have two conditions of electric field due to positive charge, electric field due to negative charge. Both we found in the in the previous slides. So from the previous slides we taken the values and substitute here, then you will get EQ plus A minus Q can be considered as, in the both the equation KQ and P caps is common. That's the reason KQ of 1 by R minus A whole square minus of 1 by R plus A whole square. So after simplification, so it will be considered as KQ of 4AR by R square minus A square of whole square into P caps. See here, do the calculation LCM. Whenever you are doing the LCM, you will get this particular value. So where KQ and P caps is common in the both the equation, and after simplification the net electric field is KQ of 4AR by R square minus A square of all square into P caps. But here we need to consider a particular condition. What is that? The value of R is highly greater than A. The value of R is highly greater than A. That's the reason we are going to neglect the value of A. We are going to neglect the value of A. Why? Because it is very small when compared to the R. So R square minus A square of all square becomes as R4. Why? Because where A is negligible, so it is considered as R4. Then the net electric field. So what is net electric field? The net electric field becomes as 4 K A Q by R cube into P caps. 4 K A Q by R cube into P caps. See here, we are what neglecting? We are neglecting the value of A. Why? Because it is very smaller to the R value. That is the reason it is considered as R to the power of 4. So after simplification, it is considered as KQ 4AR by R4 into P caps. R will be cancelled out and you will get in denominator R to the power of 3. So it is considered as 4K AQ by R cube into P caps. 4K AQ by R cube into P caps. This is the net electric field if the point is on the axis. Next, if the point is on the equatorial plane, when the point is on the equatorial plane or perpendicular bisector of the axis of dipole, the magnitude of electric field EQ at the point P due to positive charge. So what is electric field? Similarly, where you consider in this axial point characteristics, you consider positive and negative. Similarly, in equatorial also we need to consider the the electric field at due to positive charge, due to negative charge. Again, you need to consider due to positive and due to negative. So now due to positive, due to positive charge, the electric field EQ equal to KQ by R square plus A square. EQ equal to KQ by R square plus A square. Similarly, due to negative charge, E minus Q, due to negative charge, KQ by R square plus A square. Because of equatorial characteristics, the value remains same, but only the direction of the charge is changing, but everything remains same. So KQ by R square plus A square. KQ by R square plus A square. See the figure, you will be see the distance between positive and negative is 2a, and it is from center to point, the distance is R, and it is between the projection point P and positive charge, the angle is considered theta. So here this right side one, it is indicating the equatorial plane characteristics. So here you will be see properly. So our direction is indicating positive direction and negative direction is indicating by downside. So this is about the vertical line, but you need to talk about the concept of horizontal. Why? Because from the figure, the vertical components of the both the electric fields. So the vertical components are what? A plus sine theta, A minus sine theta. That is EQ sine theta, A minus Q sine theta will be cancelled out. Why? Because both are moving away from the center and both are in vertical direction. That's the reason the EQ sine theta, A minus q sine theta will be cancelled out in vertical direction components. So what we need to consider, we need to neglect these vertical components. So we need to consider about horizontal components. The horizontal components of both the electric fields will be added along the dipole. So to calculate the dipole value, we need to consider about horizontal components. So what is the horizontal component? The horizontal components E plus cos theta, E minus cos theta, E plus cos theta, E minus cos theta. So therefore, the net electric field on equatorial plane can be considered as the negative sign indicating opposite character to the vertical. That's the reason minus of EQ plus E minus Q cos theta P. EQ minus of EQ plus A minus Q cos theta P. Minus of EQ plus A minus Q cos theta P, where after simplification you will get minus 2kqa minus 2kqa by r square plus a square over 3 by 2 into p caps. After simplification you will get, evaluate yourself, you will be find the answer minus 2kqa by r square plus a square over 3 by 2 into p caps. So again same thing what we done in the previous slide. Similarly, neglecting the value of a, why? Because the value of a is very small to r, that's the reason we are neglecting the value of a. Therefore r square plus a square over 3 by 2 can be considered into r cube. Therefore the net electric field can be written as minus 2k qa by r cube into p caps, minus 2k qa by r cube into p caps. So that's about the on equatorial concept. Now the significance of the electric dipole. In most molecules, the center of positive and negative charges coincide at the same point. So positive and negative charges are coinciding at the same point, which means the distance between two charges is zero. That means the electric dipole is zero. When positive and negative charge both are coinciding to each other, the distance between them is 0. When the distance d is 0, then the value of dipole is what? The dipole moment is going to be 0. So here, where the dipole value is 0, that molecules are considered as non-polar molecules. When the positive charge and negative charge are not separated by a particular distance, then their dipole value is 0. That type of the molecules are considered as a non-polar. The example of non-polars are carbon dioxide, methane can be considered as a non-polar molecules. Here this figure is about the CO2. And next one, the molecules of positive and negative charge don't coincide. When positive and negative charges are not coinciding to each other, then dipole is not zero. The value of dipole is not zero. Then that type of the molecules are considered as the polars. So polar, and the previous one is non-polar. What is the example of the polar? That is water, hydrogen, oxygen can be considered as the polar elements or polar molecules. Thank you.